on this little activity, you just had to anagram some words, right? Anagram the word post into a variety of its 4-letter anagram equivalents. And so you were all able to find more than one way to do that in each one of these cases, right? For example, the word stop, the word stop can be post can be turned into stop by an application of this object, 1, 4, 2, 3. Or it can be done with this combination of 3 smaller objects, 1, 3, 2, 4, and 3, 4. So from an algebra standpoint, what we're going to say is that these two are equal to one another. 1, 4, 2, 3 is equal to 1, 3, 2, 4, 3, 4. Boop, like that. Right? Those two represent the same element in a group whose elements are permutations. Right? Same thing with all these other combinations that we found. Like whatsoever permutations and the group in which permutations reside will come to mean for us. However we define it, these combinations of permutations will be equal to those other combinations of permutations. Because at the end of the day, all of them turn post, both of these turn post into tops. Both of these turn post into stop, and so on. Right? And I set you a challenge here. The bonus challenge was to always try and find a version that only uses the keys on the top row, which were these permutations that only have 2 digits in their notation, combinations of them, to get you the permutation you're looking for. And you were always able to do that, which is interesting. So I want to jump over to question 2 and find out from all of you, what did you say about how it is that this notation works? So why, for example, is 3, 4 the permutation that turns post into pots? What's actually happening there? Yeah, Cam.
You're taking whatever is in the 3rd position and putting it into switching it with the 4th position.
So 3rd position switches to 4th position. Okay? And so that seems like it's enough to tell me how the 2-digit elements in here work. So what about post turning into spot? 1, 2, 3. What's happening there? Yeah, Kylie.
So for the ones that are like more than 2,
Mm-hmm.
we said that each number was like taking the position of the number to its right.
Okay.
And when you get to the end, it like goes back to the beginning.
Yeah.
So 3 takes that position.
Yep. Each object is taking the position of the next one in the line, and then when we get to the end of the line, we wrap back around to the beginning. Absolutely. That's exactly how this notation works. Okay. Then the last thing I guess I want to ask, and this goes to question 3 a little bit. You've completely decoded what we just call cycle notation for permutations. That's what we call it when we use this sort of positional parentheses notation to denote how a permutation works. So we call it cycle, of course, because it comes back around to itself at the end. Right? Then my last question is, do these permutations commute? I want to take the tops example here. Right? 1, 3, 1, 4. These are 2 permutations. If you do 1, 4, 1, 3 instead, what happens? What do you get instead?
Sopt.
Sopt, S-O-P-T?
S-O-T-P.
S-O-T-P, sopt. S-O-T-P. So what do we conclude from that? I chose the word post here because it has like more 4-letter anagrams than any other 4-letter word, I believe. But yeah, some of them are not actually words. We can call this the state of the permutation address. So what do we conclude about whether or not these permutations commute? It doesn't seem like they do in general. So here again, when we do put all these pieces together into a group, this group is not going to be what kind of group? It's not going to be an abelian group once we put this stuff together. When it comes to the commutative property in this group, of course every element is going to commute with itself and every element is going to commute with its inverse, but there's also some other interesting examples like 1, 2, and 3, 4. Those give me the anagram opts, right? And those do commute with one another, and for the reason that Colleen said, what was that reason? Why does 1, 2, and 3, 4 commute with each other?
They don't affect the same elements.
They're not affecting the same elements, right? 1, 2 is trading places between the 1st and 2nd positions. 3, 4 is trading places between the 3rd and 4th. And those two are not interacting with one another at all. We call those disjoint cycles. And we conclude here that disjoint cycles commute.
Question.
Yeah. If I know how to invert 1, 3 and I know how to invert 1, 4, how can I invert their product? What's the principle that we would have to use there? Shoes and socks. You got it. So shoes and socks would say that this inverse is equal to what? 1, 4 inverse, 1, 3 inverse. But each of those inverses is itself. Right. So one way to think about what the inverse of 1, 3, 4 is it's going to be 1, 4, 1, 3. So try it. If you do this, and then 1, 4, and then 1, 3, you should end up back home. Right? But then maybe there's a way in which you could write this as a single permutation instead of as a product of two involutions. We call these involutions transpositions, by the way. So transpositions are these cycles of length 2. All right, so last question to wrap this up. If the order of these transpositions is 2, what's the order of, say, this one, 1, 3, 4? How many times do you have to use this permutation before it becomes the identity? 3 times. If you hit 1, 3, 4, whatever key that is on the applet, if you hit it 3 times, I think you get back to post. Huh? Yep. What do you think the order of 1, 4, 2, 3 is? 4. So, last question to wrap up. How many elements are there in a permutation group on 4 symbols? How many ways are there to permute 4 elements? Those of you taking probability theory. 4 times 3 times 2 times 1. 4 factorial. 24. Exactly. So there are as many elements in these permutation groups as the factorial of the size of the set that we're permuting. So